conference. So what I'd like to do right now is to switch gears a little bit with respect to what has been shown so far. And instead of looking at the ensemble of integrated mass of a cluster, actually look at the detailed profiles of the gravitational field as we can reconstruct them. And to that end, the goal will be, instead of going to weak lensing, which we know is very well, we have seen a lot of talks on that, and we know has a very good constraint on the actual mass on the actual masses at R500 or R200. The goal will be to actually look at the shape in detail, and for that we need higher precision than what can be done with weak lensing. So we will resort to using a combination of data from X-ray and SZ through the hydrostatic equilibrium equation. And what do we do? So in X-rays, and the SZ effect, we in fact observe the same source from the physical point of view, meaning we observe the intracluster medium. From the X-rays, our primary observable is the X-ray emissivity, which is proportional to the square of the electron density, as you can see on the left-hand side for this mosaic image of the coma cluster. While for the Sunyaev-Zeldovich, what we are observing is the integrated pressure along the line of sight. Now, if we can have access to both these observations at the same time, if we can have information both on the X-ray distribution and on the SZ distribution at the same time, then we can combine them. And by doing that, we can get back to the thermodynamic properties. So we can get back to the temperature as the ratio of SZ pressure to X-ray density, to the entropy as the ratio of the SZ pressure multiplied by X-ray density to the -5/3. And then under the assumption of hydrostatic equilibrium, we can solve this equation and we can get back to the mass profile point by point. I think that's the key message I want to pass here, is that this equation is valid locally, if to the extent that it's valid, of course, which will allow us to reconstruct the mass profile and gravitational field profile, generally speaking, of our clusters over a wide range and with high statistical precision. So to do that, we started a project called the XMM Cluster Outskirts Project, XCAP, which is a former large program on XMM where we observed 12 clusters that were selected from the Planck All Sky Survey, and they are local clusters at redshift between 0.04 and 0.1 with very high signal to noise. So they are the highest signal to noise detections in the Planck survey. And what we've done was to get a large number of observations that you can see here. As an example, we have one central pointing and then 4 offset pointings in order to cover the entire cluster out to its virial radius and beyond. And here is just to show you from this nice paper, recent paper by Anna Silvia Baldi, what we can do in terms of SZ effect. These are the reconstructed Planck maps of our systems. You can see all of them are detected with very high significance. And we can get very nice measurements of the pressure profile from them because they're also nearby. So the PSF of Planck is quite a bit smaller than the extent of these systems on the sky. So here are our profiles. Just begin on the left-hand side. These are the gas density profiles we reconstructed for the 12 clusters of our sample. On the right-hand side, these are the corresponding pressure profiles, where from the pressure profiles, we have both the SZ pressure measured directly from Planck and the pressure we reconstruct by combining the spectroscopic X-ray temperature with the gas density from the X-ray. And you can see that we are spanning a very wide range in radius, over 2 orders of magnitude, meaning that when we reconstruct the mass profile from these profiles, we can really look at the shape of these systems over a wide range. So how do we do that? We put together a modeling scheme for the mass, where what we do is we start from a model for the gas density profile, which is actually a non-parametric model. And we combine that with a mass model, which could be typically an FW or an ASTO. And then by doing that, you can integrate the hydrostatic equilibrium equation, get back to the 3D pressure profile and to the 3D emissivity. Then by combining them, we get we do a full forward modeling approach where we predict the surface X-ray surface brightness profile, the X-ray spectroscopic temperature profile, and the SZ Y parameter profile, and we fit all these quantities jointly in order to get back to the mass profile. We also recently put together a new approach where we try to reconstruct the mass profile without any assumption on the shape of the mass, where here what we are doing is to reconstruct the temperature profile as with using a non-parametric method as a linear combination of Gaussians. And then with the non-parametric models for the density and for the temperature, we can again combine them and predict jointly the X-ray and SZ observables, such that we can get back to the actual shape of the profiles without making any assumption on the mass. How does it look in practice? I give you an example here for the cluster Abel 1795. Here on the left-hand side, you can see the X-ray surface brightness profile of this system and our model, which is the green curve is the PSF convolved model, and the blue one is after PSF deconvolution. On the right-hand side, I'm showing you the result of the non-parametric reconstruction for the temperature, where we have at the same time the actual temperature measured from the spectroscopic X-ray temperature in red, where you can see in the core we have good constraints from the X-ray spectroscopic data, while in the outskirts these are the temperature points we get by combining X-ray and SZ data, and there you can see that thanks to the SZ data, we can extend the range towards much larger radii than what can be done with X-ray alone. And now these are the models we get for the pressure profile on the left-hand side. And as a result, now if you've got the pressure profile, then from the hydrostatic equilibrium equation, you can get back to the mass profile, which is what you can see here on the right-hand side, where I compare the NFW reconstruction here in green with the INASTO in blue, in magenta. And the points that you can see here are the non-parametric masses reconstructed at the position of the X-ray and SZ measurements. So as you can see, we get really high quality measurements in terms of statistical precision using this combination of data. And what I'd like to get to is that what we are able to do also is to measure not just the typical NFW parameters, but we are also able to go to the INASTO profile, extend it, and measure this mu parameter, which is 1 over the alpha parameter of INASTO. And you can see the type of uncertainty we get on the shape parameter of the INASTO profile, which I think is quite striking. Now, of course, what I need to address is the question of the hydrostatic equilibrium equation. Is it valid? And what we've done on the left-hand side was to compare our masses obtained using the hydrostatic equilibrium equation to the ones we get from other methods. There are masses here from scaling relations, masses from Planck here in red, dynamical masses obtained from the velocity dispersion of galaxies here in green, weak lensing masses here, and caustic masses in blue. And this is the ratio of the other masses to ours. And you can see we are always within 10, at maximum 15% difference with the measured with the other methods, meaning we think that the hydrostatic equilibrium deviations in this sample are quite low. And we can confirm this on the right-hand side by measuring the gas fraction. And the gas fraction in purple here is what we would expect to find in terms of numerical simulations, assuming we have a good idea of what the expected gas fraction should be at the very high mass end since clusters are closed boxes. And you see that our points, which are here in blue, get very close to that, meaning we have a good reason to believe that the biases due to hydrostatic equilibrium equation are low in our sample. Now,
3 minutes left, Dominique.
Sorry?
3 minutes.
3 minutes, fine. So here are the comparison between the NFW, INASTO, and non-parametric reconstructions. And what you can see immediately is that the INASTO is doing a better job at reconstructing reproducing what we see from the non-parametric methods. Now, what we can do a little bit further, now that we have this measurements from the INASTO profiles, and what we can try to do is compare our measurements with the lambda CDM assumptions, and especially deviations from lambda CDM that would occur in the case the dark matter interacts with itself. So if dark matter interacts with itself, then what's going to happen is that it's the interactions of dark matter in the core are going to smooth out the profiles, and instead of the Caspi profiles that we expect in lambda CDM that you can see here, we expect to find flatter profile in the core like this. And this is reflected in the INASTO shape parameter alpha. What we are showing here are the results from numerical simulations, Bahamas simulations, where we change the dark matter self-interaction cross-section. And what you can see is that these are the lambda CDM values. So this is 0 actually. And this is what happens when you increase the dark matter self-interaction cross-section. Each of the points here represents one simulated cluster. And you can see that the alpha parameter increases from values around 0.18 for the CDM case to 0.4 for self-interacting dark matter with this type of cross-section. Now, here are our measurements. And what I'd like to say is that there are a number of systems here where we know we cannot do a really good comparison because, first of all, we know there are merging systems, so the hydrostatic equilibrium may be violated. Second of all, we don't know whether we are picking out the right center. So what we do is we select only the systems that are regular X-ray clusters that have a centroid shift less than this value of 0.02. And then we end up with this type of average measurements here in our systems. We perform similar analysis also in the simulated systems, where we select only the systems that are relaxed, meaning with this X of less than 0.5. And we can compare now our measurements with the expectation from the simulations for various values of the self-interaction cross-section. And what you can see is that especially our relaxed subsample, which is here in blue, matches very well the predictions from lambda CDM and is actually very sensitive at excluding self-interaction cross-section in so what you can see here is that, for instance, this value of self-interaction cross-section of 1 centimeter square per gram is very strongly excluded by our data. So what we do, we just fit a curve here between that relates the INASTO alpha parameter in the simulations to the self-interacting cross-section. And we have these points here with the curve is our blue. And right here is the values measured on average in our relaxed subsample. And we end up with this type of posterior for the self-interaction cross-section. So when we put all this together, if we use the regular subsample, we can put an upper limit of to the self-interaction cross-section of 0.13 centimeters square per gram, which is about 10 times deeper than what can be done from merging systems like the bullet cluster. Okay, so here is my take-home message. What I would like to remember from this talk is that by combining X-ray and SZ data, we can get very precise constraints on the gravitational fields of our systems. And we have selected this system where we think hydrostatic equilibrium is a relatively valid assumption, such that we can apply it and get good constraints on the shape of the gravitational fields in our clusters. The Einasto index alpha can be measured with high precision in our sample. And what this Einasto index alpha is a sensitive probe of the dark matter self-interaction cross-section, such that when we put together our measurements with the simulations from Bahamas type, then we end up with this type of constraints on the self-interaction cross-section, which is about 10 times deeper than what can be done by individual merging clusters like the bullet cluster. Thank you very much for your attention.
That's great. Thank you very much, Dominique. So we have a few questions. Some have popped up in the chat as well. So I don't mind giving you a bit of chance to answer them, since we've got the discussion section directly afterwards. So we can answer, so we'll take the questions now. So firstly, anyone who put them in the chat, so particularly I want to encourage people who are earlier career researchers. If any of you who posted in the chat want to ask a question first, you can go ahead. Then I shall return to the familiar faces afterwards. Well, so there was one question in the chat. What about the SZ X-ray peak offset? Does that affect the result of your sample?
It does, of course. And that is why we apply the criterion of selecting systems that are X-ray regular, so they have a low centroid shift. So maybe I should explain a little further what the centroid shift means. It is we take an aperture, we measure the value of the centroid of the X-ray emission within this aperture, and then we change the aperture, we make it smaller, and we compute another value for the centroid of X-ray emission, and we make it smaller and smaller, and we see how this centroid is changing when we change our aperture. And that is a sensitive probe of the dynamical state of systems, such that by selecting systems that have low centroid shift, we, in principle, are selecting objects for which the peak of the dark matter is close to the peak, to the centroid of the X-ray emission.
Okay, thank you. And then another question from the chat. In your modeling, how much does the velocity anisotropy of the gas matter? Does that cause any bias?
The velocity anisotropy of the mass of the gas would, of course, cause a bias. Again, that is the hydrostatic assumption, right? So here, so far, we are purely under the hydrostatic assumption. So if the gas has especially a high turbulent velocity, then high turbulent velocity would act as another source of pressure against gravity, and that would bias our masses low. However, how much this has an impact on the actual shape of the profiles is probably less than that. So that is one point to mention here, is that I didn't look too much at the actual overall masses we were looking at, but rather at the overall shape of the profile. And that's considering that the turbulent velocity will also be relatively homogeneous across the cluster, then with some gradient possibly, then our shape parameters should not be too much affected.
Okay, and then maybe we'll take one more question. So from Norma, if you want to unmute and ask your question, then Gary and Andrea, maybe you can ask your questions in the discussion.
Thank you. Very nice. You have clear conclusions, excluding or defavoring again, I mean, self-interacting dark matter from the Einasto alpha parameter. Now about the precisely Einasto profile and the other profile you display. We know, as you show, that these are very gaspy and so not favored by the observations. And so how do you cope with that, or which other profiles you are considering to cope with the observations? In particular, when you say that lambda CDM in the observations you show agree. I mean, this is related with some with the simulations and all what we know about it, and also about the way one treat the concentration. I mean, if you vary the concentration, if you do hypotheses on that. So thank you.
Okay, so there's a lot to say here. Of course, so the concentration we fit. We don't assume the concentration. So maybe I can go back to this type of plot. So here you see there is the posterior distributions for the anasto fit. And this parameter here is the concentration. And this is mu, which is 1 over the alpha parameter. So we are fitting the 3 anasto parameters, and we get this type of constraints for them.
But
Meaning,
for the other profile on cold dark matter, you fix the concentration because it fixed in that profile, not in anasto, but in the other.
In NFW, we also fit the concentration.
Well,
So,
that is.
You refer to this, do you? So I mean, okay, this is a plot from simulations where on this side here you have each point is a simulated system. Actually, many times you start from the same initial conditions. So you actually have the same system which is simulated with various physics. So here these are both CDM but with various physics. And now this is by changing the self-interacting dark matter cross-section. And then we take the actual particle data from the simulated halos and we fit the shape and we measure the anasto alpha parameter for each of them. And then here what you can see on this plot is the mean or median value, I think, and percentiles of each of the runs. So you can see that CDM, even when you change the physics, doesn't, the alpha parameter is relatively insensitive to that. And on the other hand, when you increase the self-interacting dark matter cross-section, you can see that the alpha value increases quite significantly. Does that answer your question?
No, but anyway, I see the point you make. I mean, in fact, I completely agree. Anasto having more parameter can fit better the observations, but not NFW, which was initially for a value of concentration. Now, adding parameter, of course, you have better fits. The question is I completely agree. I mean, your analysis is clear and shows that self-interacting cold dark matter is not favored, as already known. Now the question is about other profiles. Perhaps you can fit with the observations you have.
Well,
not just these two ones, because there are there are more parameters. There are more profiles which which are not CASPI, which are, I mean, we know.
Yeah. So in a paper by Stefano Ettore 2 years ago, we tested 5 different profiles. We looked also at the Burkhardt profile, isothermal sphere, and Hernquist profiles. And we found that none of them was providing a better fit than NFW or Inasto. So I mean,
okay, I think we should.
Profiles are still favored.
Okay, thank you, Dominique. I think we should just stop there now so we can move on to the next talk. So thanks again for your talk there. So if you stop your screen share, and then the final talk of the session is by Florian Ruppin from MIT. And we're going to be hearing about a different aspect of joint X-ray and SZ analysis. So take it away, Florian, and I will hold up my sign when you've had 9 minutes.
Okay, can you all hear me well and see my screen and my pointer moving?
Yes.
Okay, great. So hi everyone. I'd like first to thank the organizers for giving me the opportunity to present this talk. I'm actually now a postdoctoral researcher in the Euclid collaboration at CNRS, but all the work that I'm going to present now has been done during my first postdoc at MIT in the team of Michael McDonald, and it's tackling the issue of the impact of gas physics on the cluster mass scale from joint X-ray Z analysis within the South Pole Telescope and the MATCAUS collaboration. So first, I'm going to briefly talk about some systematic uncertainties that are going to affect the next generation of cosmological surveys with clusters. Then I'm going to talk to you about the high angular resolution studies that we're doing targeting the ICM at redshift higher than 1 in the MATCAUS survey. And I will finish this talk by talking to you about the recent results on the evolution of AGN feedback during cluster growth in the SPT collaboration. So here, what you can see in this equation is the expected halo abundance for a given mass and redshift at a significance level higher than some threshold. And so you really know this equation, but you can see here the first term is the selection function. The second one is the well-known mass observable scaling relation that is inducing most of the systematic effects in our cosmological studies. The co-moving volume is slightly dependent on cosmology. And here, what I would like to emphasize on this slide is the importance of the cluster mass function for the next generation survey. Indeed, this mass function is calibrated from numerical simulations, and in the past, we've mostly used mass functions calibrated from n-body simulations. Here, for example, you can see the cosmological constraints obtained on sigma 8 and omega m from the Planck collaboration with using 2 different mass functions. And while the difference here is not significant at all, it has been shown in several studies now that this difference is going to be significant for the next generation surveys, such as Euclid or the Ruppin LSST. Furthermore, I would add that the hydrodynamic simulations that also include the gas properties and feedback from active galactic nuclei, for example, predict different cluster abundance for the same cosmology. Here you can see on this plot from Cui et al. 2014 that the expected halo number density for hydrodynamic simulations that include AGN feedback, so the green curve here, is about 20% lower than the one expected from a dark matter only simulations for the same cosmological parameters. And at present, we don't have enough knowledge on AGN feedback and heat dissipation within the ICM to have a precise view of what the cluster mass function should be. So we need observational priors to improve our cosmological simulations and reduce the systematic effect. So to do that, we need to target some regions of the mass redshift plane and do a detailed ICM physics characterization. So we start from a blank page here, an empty mass redshift plane with an upper limit fixed by cosmology. And we can fill up this plane with some cosmological surveys. Here I'm showing you the SZ detections that were here in 2019. And we all know some well-known samples that have been characterized, such as the REXAS sample, the NICA2SG large program sample that is going on. Some clusters have been studied at high redshift from McDonald in 2017. Here I'll show you the 2 samples from the XMM Heritage program. I'm forgetting a lot of samples here, but I just want to show you that we start to have a very good picture of cluster physics at redshift lower than 1. However, due to the small sensitivity, the limited sensitivity of our generation of extra observatories, the picture is not that clear for redshift higher than 1 clusters. Unfortunately, this is where most of the constraining power for the dark energy equation of state is going to be for the next generation cosmological survey. So we need to have a better understanding of cluster astrophysics there to limit our systematic uncertainties for Euclid and LSST. So the way to go forward is by combining X-ray observations that are going to be low signal to noise at such high redshift with SZ observations at high angular resolution. But to do that, we first need to have a large sample to study. So this is why we can rely on optical infrared surveys to detect high redshift clusters that we can then follow up with high angular resolution SZ instruments such as NICA2 and Mustang 2 that are both located in the northern hemisphere. So the MATCAUS survey is the massive and distant clusters of WISE survey has been realized on the whole sky using the WISE satellite in 4 wavelength bands in infrared. And the cluster detection is made by looking at galaxy over densities, such as, like you can see in this figure, using both the WISE and optical data from previous surveys, and using the PZ-wave algorithm that has also been selected by YouTube. The confirmation of those galaxy over densities as bona fide clusters is made by looking at Gemini and Keck spectroscopy to get the redshift of the cluster members. And for some of the clusters, we also have a NESI confirmation by Karma, the Karma interferometer. And you can see here a typical map obtaining NESI with Karma, for which we can extract NESI map mass for scaling relations. And based on those cluster detections, we have constructed the sample, a first sample of 10 clusters to be followed up at high angular resolution in SZ and X-ray using the NICA2 and Mustang 2 SZ instruments and the Chandra satellite. So the 10 clusters that we have chosen are shown here in red in the mass redshift plane. And our goal is to study merger dynamics and evolution of ICM thermodynamic properties at redshift higher than 1. All these proposals have been accepted and all the observations have been completed in 2021, really recently. So here I'm showing you the typical maps that we get for those 10 clusters. Here you can see, so I'm showing here the case of the most massive cluster in the sample, MOJ1142 at a redshift of 1.2. You can see here the map that we obtain in infrared using Spitzer. Here, the one that we obtain in X-ray with Chandra, and here the one in Z at 150 gigahertz with NICA2. What we can see for this cluster is that we can clearly see 2 main galaxy structures that we call A and B, and the X-ray peak that is shown here with the blue cross coincides with the brightest cluster galaxy that is at the center of the A substructure. However, what we see in the SZ map is that the SZ peak that is shown here does not coincide with the X-ray peak shown with the green cross there. It is otherwise located between the A and B substructures, which is a clear sign of a merging event going on between A and B, which causes this overpressure region that is shown with the SZ map here. So just by looking at the map, we can already say that this cluster is most probably an ongoing merger with a cool core located at the location of the X-ray peak. What I would like to add is that most of the clusters in our sample of 10 clusters look as disturbed as this one. So it's really different. The view at redshift higher than 1 is really different from the one that we get at low redshift. So we build a dedicated pipeline to analyze jointly the X-ray Chandra data and the SZ, NICA2, and Mustang 2 data to recover both the density profile and the pressure profile of those clusters. And among other things, we can perform an hydrostatic equilibrium analysis to recover the mass profiles of those clusters. And here you can see the mass profiles that we have extracted for this particularly disturbed cluster in 4 different sectors centered on the SZ peak, so the centroid of the cluster. And we've done that in order to study a potential impact of the merger dynamics on the mass reconstruction that we have. And what we can see is that a simple spherical model for such disturbed cluster is obviously not adapted and leads to huge systematic uncertainties on the total mass, as we see here from the scatter of the mass profile in the outskirts. I can show you here the different mass proxy that we have from different scaling relation compared to the hydrostatic estimate that we have here. And while the statistical uncertainty on this estimate in green here is small, the systematic uncertainty computed from the scatter of the mass profiles there is really huge. So we need to improve our ICM models in both astrophysics and cosmology analysis in order to reduce the systematic uncertainty on the calibration of the mass observable scaling relation at such high redshift. So we're not doing only that with this sample of clusters. We are combining the Chandra and NICA2 Mustang 2 data at the map level in order to obtain the temperature maps that you can see here. Here's the temperature map of the cluster that I've just talked to you about, in order to correlate the temperature fluctuations that you can see here with the galaxy distribution, and thus reconstruct the merger dynamics of those clusters. We are also cross-correlating our ICM thermodynamic properties with the AGN radio emission that we get from VLA in order to study the AGN feedback at high redshift. We use the X-ray spectroscopic information that we have from the Chandra data in order to study metal enrichment. Yeah, thank you. And of course, we're studying the cosmology point impact that this small survey will have by estimating the hydrostatic masses and comparing them with the richness-derived masses to study a potential redshift evolution of the mass-richness relation and study selection biases at redshift higher than 1. So overall, the characterization of this sample will give us a detailed view of the ICM physics in a sample of redshift higher than 1 clusters for the first time, but we really need to push this investigation even more for the next generation cosmological surveys. And now I'm going to switch collaboration and talk about the evolution of AGN feedback during cluster growth in a sample of SPT clusters. Going back to this plot of the mass redshift plane, I'd like to say that while very interesting in their own rights, none of the samples that are shown here in color can be used in order to study the redshift evolution of the ICM properties for clusters that follow the same evolution history. Indeed, it has been shown in multiple papers now from simulation, and especially from factory data in 2010, that clusters are growing in the mass redshift plane by accreting matter and merging events with surrounding substructures following those diagonal lines in the mass redshift plane. So in order to study the redshift evolution of ICM properties of clusters that follow the same evolution history, we need to select clusters that follow those diagonal lines. So that's what we did. We selected a bunch of SPT clusters that lie between those two diagonal lines, and we proposed for Chandra observations to get an ICM, the ICM properties of those clusters. So for the low redshift clusters, we get moderate signal to noise with about 1,500 counts per cluster. But obviously for the low mass and high redshift clusters, it is much more difficult because of the limited sensitivity of the current X-ray observatories. So we get about 150 counts. And to analyze the ICM properties of these clusters, we need more information. Fortunately, those clusters have been selected using the SPT catalog. So we already have the SZ signal, some SZ signal for these clusters in the form of the integrated compound parameter. And this is really improving our analysis. Here you can see the density profile that we are extracting for typical X-ray analysis with 170 counts. And most of the uncertainty here is coming from the lack of constraint on the ICM temperature, because the X-ray spectrum that we get is really compatible with the background spectrum. But by adding the SZ signal, we get a good constraint on the ICM temperature. And so we are able to reduce this systematic uncertainty and gain a factor of 5 on the error on the density profile. And from these constrained density profiles, we can extract the density at 10 kiloparsec in order to count clusters in different bins of redshift and estimate the cool-core fraction. So you can see here on this plot the evolution of the cool-core fraction as a function of redshift for 4 different bins, and we concluded that the cool-core fraction remains constant during cluster growth over the past 9 gigayear, which is in slight tension with what is obtained from the most recent magnetohydrodynamic simulation, TNG, that is showing that this cool-core fraction should increase with redshift. So this is really constraining for the simulation. And finally, we are adding some radio information to the picture using the data from the Australian Telescope Compact Array that you can see here. And by fitting the radio signal that we find in the AGN at the center of the BCGs of those clusters, we can estimate the spectral energy distribution of those AGN. And from these SED, we can estimate the AGN jet power that we find in this cluster and correlate it to the ICM cooling rate that we can estimate from the analysis of the X-ray and the SZ data. And on this plot, you can see all the points that we are adding here in red and purple to the picture that was already existing, so the blue points that are shown here. And by fitting jointly all those data points, we can get a very tight constraint on the feedback cooling equilibrium. And we have shown that this equilibrium has been going on since redshift 1.5 and is really tight. So this is also a new constraint to add to the simulations. So to conclude, I would say that combining X-ray and SZ data gives us a way to probe the ICM physics at low mass and high redshift. We've shown that high angular resolution SZ gives us a way to map the ICM properties without relying on X-ray spectroscopy. The integrated compound parameter is some SZ information that everyone can have for free because it's in most SZ cluster catalogs, and it can act as a constraint on the mean ICM temperature. We are providing a detailed characterization of merger dynamics in a cluster sample at redshift higher than 1, and we have shown with SPT that the cool-core fraction is constant with redshift over 9 gigayear, and that the equilibrium between radio mode feedback and cooling has been going on since redshift 1.5. So those are observational priors that can be used to improve cosmological simulations. And the takeaway message here is that joint X-ray SD analysis are the bridge between XMM and Chandra and the next generation X-ray observatories such as Athena and Lynx to understand cluster astrophysical systematics in our cluster cosmology analysis. Thank you very much.
Thank you, Florian. So I think we can take one or two questions before we segue into the discussion session. Does anyone have a question for Florian? Yes, Dominique.
Hi, nice talk. One question about your comparison to the cool core fraction. So first of all, one thing to notice that people have different definitions for what they call cool core and how it evolves with time. So
yeah,
have you applied the exact same definition to the simulations and to the observations? And second of all, how confident are you that the physics that is included in the simulation is actually enough to predict this type of relation when we know that especially what's going on at the core in the central region of clusters is very difficult to model numerically speaking?
Yeah, of course. So first of all, you are completely right. There are multiple definitions of what the cool core is, whether you rely on the entropy flow, the density, or the cuspiness of your X-ray surface brightness profile. There are multiple definitions. Here, when I'm comparing the data with the simulation, I'm using the same definition. So this curve here in purple here has been obtained by using the ICM density as a proxy for what a cool core is. So this is consistent. But of course, if we use a different definition, the value, the normalization of this could be different. So it's not really the normalization that we were interested in, but rather the evolution of the cool core fraction with redshift. And your second question, so was about the modeling of the subgrid physics that is inducing this constraint on the cool core fraction. Well, the only thing I can tell you is that if the simulation were right, well, we would get a constant cool core fraction with redshift up to redshift 1.2. And so what we can say here is not how simulations should change their model in order to fit the data. We need more information to do that, but that the current view that we have for the subgrid physics is not adapted to represent AGN feedback in clusters up to redshift 1.2. I mean, we shouldn't have this kind of evolution from redshift 0 to redshift 1.2 at least.
Maybe I could just follow up quickly. So does the Barnes model, is that telling us that all clusters are cool cores at a redshift of 1.4?
No. It's oh, you mean?
Well, the purple line, well, it goes to a fraction of 1.
It's a simple model. I don't think that I mean, yeah, that's true that it's even going up to higher than 1, but it's the model that they used that it to fit their data in the data in the simulation was a linear fit, so obviously it's going to go above 1. But the fact that it's increasing is already something that's not that shouldn't happen.
Maybe it's just showing that the increasing density of clusters. I don't know. I'll be a bit cautious.
Well, if the core density increases and they use the same definition as we did to define a cool core based on the central density, what we can say from observations is that it shouldn't. The core density shouldn't increase with redshift like this. Yeah.
Okay. Thanks, Florian. So I think I need to share my screen now. So maybe if you stop sharing yours, and hopefully I can share mine. And we've not got too long for the discussion. I don't want to go on too long because I'm sure everyone is tired of looking at their screens. But let me try and do this. Right. If I share that.